Yeah, thank you. Thank you everyone for joining. So today I will be reporting some work that are still work under progress. And this is joint work with Matt Holzer from George Mason in the US, Lars Zimmer in Germany, in Bremen, and Arne Schill in Minnesota in the US. So the aim for today is going to be basically trying to introduce you to the concept of remnant instability if you have never encountered that. And for that purpose, I've decided to focus on one case study. So I will be considering a system, a couple systems. So there will be two components, a U component that will be the classical, I would say, Fisher KPP equation in a moving frame with wave speed c that I will always take positive. And it will be coupled to a second component denoted V here, which is just the linear Swift-Wenberg equation, which is well known and well used when you try to study and or model pattern formation and say Turing bifurcation or stuff like this. So the idea here is, sorry, I totally messed up. So it's about studying fronts that are invading some unstable states. So here, what I will be considering, these are just trivial fronts. So I will just be setting V equal to 0 and just having a front from the Fisher KPP equation. So these fronts are just well known, and I denote them UC, where C is the wave speed. And we know for sure that there exists such monotone fronts that connect 1, 0 to 0, 0 for any wave speed larger than some critical wave speed that is linearly determined. And here it's just given by 2 times square root of d f prime of 0 and f prime at 0, just to fix idea, it's this specific nonlinearity f prime at 0 is just alpha. And so it satisfies this traveling wave ansatz with the boundary conditions that I just mentioned. And so the question that I want to address or try to give some hint of what can happen, it's about trying to, what can we say about the asymptotic stability of solutions of these traveling wave solutions. So I will be taking perturbation around such a solution and see what we can say about this perturbation. And obviously we have lots of parameters here in the system, and I'd like to have a systematic answer for each parameter. So here alpha is going to be positive, d is going to be positive, mu is negative, beta here will not matter that much. I just want it to be non-zero, and here the wave speed also is going to be positive. And well, it will always be above that specific value. So already some remarks about this time model is that the V equation is always uncoupled. And so we know exactly what happens in that case. And we know that 0 attracts all solution. It's stable, and we even get how fast we would go back to the rest state. So here I'm just giving an hint of what's happening. It's not difficult to prove it, and it's not the point. The point is really the coupling. Though if you don't have coupling, meaning that if you allow for a second beta to be equal to 0, then the system is totally uncoupled, and the first component is just the usual Fisher KPP equation. And for this one, we know that depending on whether or not the wave speed that you take is larger or equal to this critical linear spreading speed C star, then you get different type of results for the stability of the fronts. So when they are supercritical, meaning that C is strictly larger than C star, we know these are all results by Settinger in the 70s that we get exponential asymptotic stability with no shift, and you need to take care of the fact that you're invading an unstable state. We'll come back to that later, but you need to work in some exponentially weighted spaces. The more interesting part is about the analysis of the critical fronts. So here we're in the pool regime, and C is equal to C star. We also get asymptotic stability, but this time we don't have an exponential decay in time of the perturbation. It's only algebraic, and we know that the optimal rate of decay of the perturbation is given by this t to the minus 3 alpha. There is still no shift, and you also need to work in some exponentially weighted spaces. So these results, this sharp stability result is due by Gallet in the 90s, and recently I've been working with Matt Holzer trying to get different proof and trying to see if this type of algebraic decay rate is something that is generic in some sense. So in what follows, just because it's the most interesting case, I will only be considering the case when C is equal to C star and the critical pool front. And once again, we want to determine its nonlinear stability against well-chosen perturbations. So the very first thing that I will be doing is just looking at linearizing the system near the unstable steady state 0, 0. So this just means that I'm linearizing near plus infinity, and there I get a triangular operator, limiting operator that I call L plus, and it's on the diagonal, I get the linearization of the Fisher-KPP equation near 0. So it's just given by this second order linear operator. And for the V component, as it was already linear, it's just the operator itself that was defining this, this equation. So this is just the Swift-Sternberg equation. So when we talk about spectrum of constant coefficient operator of that form, we know that their spectrum, if we see these operators on L2 spaces, it will only consist of essential spectrum. So essential spectrum in that case of the full operator, it's going to be the collection of the two essential spectra for each operator on the diagonal. And they're just given by parameterized curve in the complex plane. And basically, they're just obtained by taking the Fourier transform of the symbol here. Okay, so this is well known. And what we get directly from that, just because of the fact that we're here taking mu negative and alpha here is positive, we're getting that always the essential spectrum coming from the Swift-Sternberg equation is always stable. There's real part for each element in it that is less than 0. On the other end, we know that as alpha is positive, we know that the essential spectrum coming from the KPP equation extends to the right half plane. So this is not, this is well known, and we know that we're invading an unstable state, and this is how, this is one manifestation of it. So how do we handle that at this linear level? Well, what we do as usual to recover stability is that we'll be working in some different functional spaces. So instead of working in L2, we work in L2 with some weight, hoping that the weight will allow a larger class of functions so that we'll recover stability. So in that case, we can define this weighted essential spectra exactly the same way, just by conjugation with the exponential to some power eta, which is a real number. And once again, because the operator has still constant coefficient operators, we get that their essential spectra are just parameterized curve in the complex plane. And so it's just a trivial computation to see that once you're in these exponentially weighted spaces, the two essential spectra are shifted that way. So I'll give some illustration of what really it means, but just from this, this computation, what we get are the following two remarks. So the first thing is that if we focus only on the Fisher-KPP equation, we just see that its most stable point occur when the wave number here k is equal to 0 at some given, say, optimal weight. eta that is just equal to minus c over 2d. Well, this is just looking at this quadratic polynomial. And in that case, when we pick this specific optimal weight, we just get that the essential spectrum is just on the real axis and extends to this value. On the other end, we can compute the rightmost point of the essential spectrum for the V component for the Swift-Steinberg equation. If we take its real part, this is given by this value. So what can we say or infer from that? Well, very easily, if now we come back to our main problem, that is, we want to study the critical proof front, so meaning that C is not any value, it's precisely C star, so 2 times square root of D alpha, we directly get that we need the optimal weight corresponding to it, so minus C star over 2D that I denote eta star here. And it's a trivial computation to check that in that case, the weighted essential spectrum is just the negative half line. So we see that we managed to stabilize the essential spectrum, but we could not strictly stabilize it. It's only marginally stable in the sense that 0, I mean, it still extends to the imaginary axis at the origin. And to ensure now that the V essential spectrum remains stable, we also have to guarantee that mu is less than some critical value that is given by, I mean, that depends on alpha and D. And I will be denoting that critical value mu rem. And so really the question and the point here is that you can find obviously parameters D and alpha for which and mu for which this inequality is not satisfied. And you cannot stabilize at the same time the V component and the U component. And this is really what's typically the definition of being remnantly unstable. So you cannot find for any weight, you cannot stabilize the essential spectrum. And so you need to develop or to do something else to study the stability of the traveling fronts. So this is really the question, and here are just 2 cartoons on how essential spectra moves around with these weights. So on the left-hand side, this is for the KPP equation. On the right-hand side, this is for the Swift-Steinberg, and I precisely picked parameters for which stabilizing the KPP equation. So we start here when eta equal to 0, and we go up to eta star, and we've reached the negative half line. And at the same time, when we do the same thing for the V component for the Swift-Steinberg equation, so eta equal to 0, this is the dark blue curve. And when we increase eta, say up to eta star, we see that the essential spectrum crosses the imaginary axis and becomes unstable. So really the typical situation that I want to study is exactly this one, when we cannot find weights to stabilize the essential spectrum and still be able to say something about the stability of the traveling fronts. So just because I will need some more material, I will also need to introduce another type of spectrum, which will be the absolute spectrum. So far, my definition of remnant instability, as I've said, is that I cannot find any weight to stabilize the essential spectrum of my operator. And so in that case, we just say that the 0 state, the invaded state, is remnantly unstable. So I will also need to talk about this type of spectrum, so the absolute spectrum, which was introduced very thoroughly in 2000 by Sandstedt and Schiel. And basically what you need to do to compute the absolute spectrum, you take the 2 dispersion relation of each component and you form the dispersion relation of the system. So this just relates temporal roots to spatial roots. And so you have a polynomial of order 6. So you get 6 roots, and each of these roots that I denote nu j, you just arrange them, say, from nu1 to nu6 just by increasing real parts. So you can always do that, and you count them with multiplicity, and you say that lambda, a complex number, belong to the absolute, so-called absolute spectrum if the real part of the third root counted that way is equal to the real part of the fourth root. And I will explain later on why the absolute spectrum matters. I will also need to introduce two more notations. These are just double roots of the dispersion relation. So double roots are double roots of the dispersion relation in the sense that your root and also the derivative of the dispersion relation with respect to nu vanishes. It's simple if you satisfy these non-degeneracy conditions. We say that a double root is pinched if when you solve now for lambda and you let the real part of lambda goes to plus infinity, then each root goes either in real part to plus infinity or to minus infinity. I mean, I will not be talking too much about pinched double roots, but they're somehow important here. And another definition we've just seen before, that our dispersion relation is formed of the product of two dispersion relation, one from the U component, one from the V component. And I will just say that I have a resonance pole, so it's when we get a double root when one root comes from the U component and one root comes from the V component. So why talking about absolute spectrum and double roots? Well, it's, as I was saying, when we look at spatial eigenvalues, which correspond to solution, trivial solution of one that form, so e to the lambda t nu lambda x, we are solving the dispersion relation. And if we manage to always be able to consistently separate these collection of roots by real parts along a curve that would go to plus infinity in real parts, whenever we're not able to do that, when this consistent splitting breaks, then this means that we're an element of the absolute spectrum. So with that definition or that way of saying things, we just see that having stable absolute spectrum, this means somehow that we can stabilize, or that there exists a continuous choice of exponential weights so that lambda does not belong to the essential spectrum in that exponential weight. And if we say that and we take a negation of this, this means that typically unstable absolute spectrum will imply a remnant instability because we'll not be able to find any weight to stabilize the essential spectrum. I was talking about double roots. I just want to mention that absolute spectrum form curves in the complex plane that terminates in double roots. So this is why double roots play an important role. And when they're pinched, typically they lead to instabilities, either branch points or poles of the resultant kernel. And so if you get unstable pinched double roots, this will typically lead to pointwise instability. And so as a conclusion, we get that if we manage to get unstable pinched double roots, then we'll get unstable absolute spectrum, but also remnant instability. So we get these relations. And the main informal contribution of our analysis is that we managed to decompose parameter space. So here by parameter space, I mean d alpha positive, mu negative into four sets that I call RST for stable, RM for remnant, RAB for absolute spectrum, say, and RPW for pointwise unstable. So the first region is where the zero state is not, it's stable. So it's not remnantly unstable. There is no unstable spectrum and no resonance pole. New rem is when you're remnantly unstable, but you get stable absolute spectrum and no resonance pole. The region R abs is when you're remnantly unstable, and also the absolute spectrum is unstable, but you don't have unstable resonance pole. And the last region is when you get unstable resonance pole, and we've seen that this implies that your absolute spectrum is unstable and that you're also remnantly unstable. And so our main result is to provide and prove the asymptotic stability of the critical fronts precisely in the region where there is no unstable resonance pole, and obviously we're not in the trivial region where a previous result could apply. And furthermore, we could provide analytical boundaries between these regions. And to conclude, because I think that my time is already over, I just want to mention that our proof, to prove this asymptotic stability, they relies on pointwise semigroup method that we somehow reintroduced with Matt Holzer in a previous analysis. So these are well-known methods developed by Peter Howard and Kevin Zombrun, say 20 years ago now. And thank you.
Thank you very much for a nice talk. If anyone has any questions, you're welcome to raise your hand or put them in the Q&A directly below. I mean, I guess I can ask a naive question while we wait, which is, if I have a front which is remnantly unstable, would I observe this if I had, say, a numerical realization? Would I see the front speed change or otherwise?
Yes, that's a really good question, and I definitely did not have time to talk about it. And so the main difference is that in terms of stability, so there is a difference in terms of numerics in between being in the remnant part and in the absolute part of my regions. And I have some illustration for that. It's given here. So in numerics, when you're either in the stable part or in the remnant part where the absolute spectrum is stable, you see the front that is stable in your numerics for all time. However, when you're in the part where the absolute spectrum is unstable, your numerics are kind of defeating you in the sense that after some transient of time, in your numerics, you see a faster invasion front. Though you have just proved, I mean, our main theorem says that the front is always stable. So in our analysis, we propose, or we get a conjecture. So first, we're able to determine analytically what is the speed of this faster invasion front. And we also have a conjecture that this is due to runoff error in numerical simulations. And we demonstrate that. And why this is related to absolute spectrum, I just have one further illustration. It's like maybe, so which one? So does not really matter, but we're in this situation where so this is in dark red, this is the absolute spectrum of the problem. So you see it's unstable here. And in numerics, we see that after some transient of time, the front becomes to be unstable with a faster invasion front here. The wave speed of that front precisely corresponds to the wave speed for which we can stabilize the absolute spectrum. So here, this cartoon is just the same absolute spectrum, but now for a different wave speed, which is precisely the wave speed of this faster invasion front. And we see that we managed to marginally stabilize it. So I don't know if that answered your question.
No, that's perfectly fine. So you have about 30 seconds.
Okay,
Can you comment very briefly on another question, which is if these can be extended to the spatially non-autonomous setting? So for instance, radially symmetric problems. But you don't have very much time. So if not, we can move this to a discussion later.
Yeah, so I would have to think more thoroughly about it. But in a radially symmetric setting, you don't really have the existence of this traveling wave. They would be only there asymptotically, so it's a different problem. I would be eventually able to say something about, say, planar fronts. So they would be constant along a transverse direction, but in a radially symmetric setting, I'm not sure I can say something here.
No worries. Fantastic, fantastic talk. Thank you very much for the rushed question.